Hello everybody, welcome to this evening semi-plenary. So speaker tonight is Professor Jong-Hwan Kim. He received his PhD degree in electronics and engineering from Seoul National University in Korea. Since then, he has been with the School of Electrical Engineering at KAIST, the Korea Advanced Institute of Science and Technology, where he's currently a professor. He's a chair of the robotics program at KAIST and also an adjunct professor of Griffith University in Australia and Chongqing University of Technology in China. His research interests include machine intelligence learning, intelligence technology, and ubiquitous and genetic robotics. He's the founder of FIRA, the Federation of International Robot Soccer Association, and also IROC, the International Robot Olympiad Committee. Professor Kim was a recipient of the Science and Technology Award from the President of the Republic of Korea in 1997, and he has been elevated to the grade of IEEE Fellow in 2009. So let me remind you that due to the room configuration, we cannot take questions during the talk or after the talk, but that you will be welcome to interact with Professor Kim on the podium just after. Professor Kim, the floor is yours.
Okay, thank you for your kind introduction. My name is Jong-Hwan Kim. My talk is on task intelligence of robots. Contents as follows. Firstly, motion intelligence and active knowledge acquisition and adaptive knowledge application, agent-embedded robot, and Xiaomi's robot, and finally, AI World Cup. So motion intelligence is based on computational intelligence and artificial intelligence. MI could be materialized through the intelligence technology. So as you might know, these days, machine learning has been applied to various fields, medicine, biology, media, entertainment, and autonomous machines. So MI is aiming at reaching the level of human intelligence through the machine intelligence learning. So here, machines can learn our reasoning mechanism of the multi-criteria decision-making process here. In this simulation environment, for a given context, partial evaluation is obtained respect to criteria. And along with these partial evaluation values, our preference is used for this decision-making process to select a proper behavior. So this simulation data could be used for training this memory system. And then the machines go through the real experience. So for a perceived context, related event gonna be retrieved and executed, and then user response are going to be fed back to this memory system to tune the memory contents. So intelligence learning is to construct a developmental memory system. So from the next technological wave, the next technological wave should be intelligence technology, INT. Judging from this hierarchy, it is quite trivial. Information is based on data, and knowledge is the position of the information and facts, and intelligence is the ability of manipulating information and knowledge. So INT is the intelligence operating technology from sensing and thinking to action. So thinking of this STA machine, we need this intelligence operating architecture that is inspired by our base functions of human brain. So that is the perception part, memory part, internal state part, reasoning part along with learning module and the execution part over there. So based on this IOA, we can implement various intelligence, such as cognitive intelligence, ambient intelligence, social, behavioral, genetic, collective intelligence. However, today here, I'm going to give more focus on this task intelligence. Task intelligence is composed of two processes. One is the active knowledge acquisition by storing learned knowledge in a memory, and also adaptive knowledge application by retrieving the learned knowledge from the memory. So these tasks could be carried out by these robots, okay? Here, like this way. So for the requested service, to serve this requested service, the robot need to have the knowledge how to serve this requested service, and the knowledge should be retrieved if the service is requested. So here to store such knowledge, this long-term memory is very much important. So I think this long-term memory is the flower of the machine intelligence. So here, quite sensitive. So robot is learning this task sequence from the human demonstration. That is the active knowledge acquisition process. And then by retrieving the learned knowledge, it carries out the requested service like that way. So here, active knowledge acquisition and adaptive knowledge application. So this human demonstration should be learned, should be stored into its long-term memory. So for this active knowledge acquisition, I use this learning from demonstration. So to learn a task sequence like this one, the objects and the behaviors should be recognized from the scenes. So in this research, I used the RGBD plus thermal image sensor, RGBDT sensor. So for using this RGBT sensor, some calibration is needed between the RGBD and the thermal sensors. So that is the thermal image sensor, and that is the RGBD sensor. So the position, that is the RGB image. Position of the hand should be calibrated between this thermal image and RGB image. So for this purpose here, that is the raw image from the RGB sensor, and that is the thermal image, and that is the binary marking process, and then we have this contour, and then we have this convex hole, and those four green dots is the convex defects. So that is the RGB image, and down bottom side that is the thermal image. So the thermal image, the pixels of those 5 points should be calibrated to the RGB image, 5 fingers over there. So the pixel position of thermal image is mapped to the RGB pixel position through this calibration matrix. So here, the objects are recognized, and by using the thermal image sensor, the bowl with cereal is recognized, and the milk is poured into the bowl, and then the bowl with cereal and milk is recognized. So that is advantage of using the thermal image sensor. And the behavior should be recognized for the learning from demonstration. So hand is easily recognized, and of course, objects are recognized by using the RGB image. And then this behavior also recognized by using a deep neural network. So that is the, pouring behavior and putting down behavior and grasping behavior. Those behaviors could be recognized by using this LGBT sensor. And here, for example, prepare juice and cereal task. And this sequence, task sequence should be memorized into the memory. But as you can see here, if the event sequence is longer and more events should be, tasks should be stored in the memory, and then you have this dilemma. Stability plus the dilemma. How can you continue to quickly learn new things about the environment? That is the plasticity issue, and yet not forgetting what you have already learned. That is the stability issue. So for learning the new events or new tasks, the memory should be flexible, should be plastic. Yet the learned knowledge should be kept. So to solve this stability plastic dilemma, I use this ART network. So the learning process is as follows. Firstly, that for this input vector, activity vector could be obtained, and then there is code activation by using choice function like that one. And then each node has been activated by this match. And then through this code competition among those nodes, this one gonna be selected like that one. And then after then, template matching are gonna be tested. So if this value is larger than resonance parameter, and then the next step is template learning. Those ways are going to be updated. So that is the template learning process by using this equation. And if no resonance, resonant node there, and then a new node should be added like that one. So it means it is developmental network. So I chose this adaptive resonance network for our research, for designing this integrated long-term memory. So this part is the deep ART network, episodic memory. This part is emotional memory, and this part is the semantic memory, that is the procedural memory. So as you can see here, deep ART, so that is the input field, event field, and episode field, and daily episode field. So by adding more field over there, we can make monthly episode field, yearly episode field. It means we can make deeper ART network. So that is the episodic memory. And we solved some limitations of the existing episodic memory. So for example here, case event is stored, encoded into this network. That is the case event, event has been encoded over there in this event field. And we proposed the 3 channels for encoding the temporal sequence, temporal information. So that is the case event has been encoded over there. And for the next event, by following the similar same process that has been activated, encoded, and that is the previous one, case 1, and that is the currently activated event. And then this temporal information sequence is stored into here, into this node as an episode. So here in the morning, after jogging and cooking some food, so there are for example, 2 events, and these 2 events are stored into here, into this node as an episode. So that is the episodic memory. Of course, these events could be retrieved. And so this one is the test performance of this robot MyBot by retrieving the stored task sequence. Firstly, grasping the green box and place it to the box C over there. So this kind of task sequence is retrieved from its task episodic memory. And before doing this behavior, in this 3D octomap, the collision avoidance is checked. If it is confirmed free of the collision avoidance, and then it is carrying that task over, that event over there. So that is the task performance referring to the learned memory in its episodic memory. And the other one is the semantic memory. So at 10 p.m. and fried chicken, if the user requests, give me something to drink, and then robot think of these possible candidates in the refrigerator by using this category search and object selection. So firstly here, target category search for those possible candidate objects. So that one goes to the Yago server, and we get the class ownership vector, goes to the ART tree, and then this one, Cape North, is classified as alcohol, and then again classified into liquor, and then finally vodka. So a target category for this Cape North is vodka. And likewise, the rest is classified as coffee, beer, and soft drink. Okay, that is the category search. And then with this category, from the vodka to the soft drink, and this situation, and by using Instagram, the number of hashtags are counted, and then this conditional probability between chicken and vodka, and chicken and coffee, and so on and so forth are calculated like that one, and we can get the time plot for his habit, and we can get this probability node like that one, such that that is the highest. So robot can recommend this beer to him in this situation, 10 p.m. and fried chicken. And the next one is the emotional memory. So that is the event having the this Korean pasta, and that is the event channel over there, input field over there, and he had a very good emotional state, happy, for example, happy emotional state. So event along with internal emotional state is recorded into this episodic memory, episode node. And then if the robot recognize this, having this food is recognized, and then related episode retrieved, and that is the episodic, emotional channel. So from the strength of these emotions, the emotion is predicted. So this happy moment is retrieved, predicted. So the robot shows happy reaction when it watches the owner, the user having some food like that one. So that is the emotional memory. And the last one is the procedural memory. So we designed this procedural memory by using recurrent neural network. It's implicit memory. So we do these behaviors without any conscious thinking. So here, riding a bike or tying shoes. So from the learning from demonstration, these trajectories should be learned So for that purpose, we used these two coordinates. One is the egocentric coordinates. The other one is object coordinate, coordinate, centric coordinate. So this behavior gonna be learned into in this coordinate, and also decoded into this robot-centric coordinate for performing this behavior. So for the purpose, this encoder from this egocentric coordinate to the this object-centric coordinate, that encoder is needed, and also decoder is needed for performing that behavior. In between, generator is provided. So of course, you can do this transformation by using transformation matrix. So from the egocentric matrix to the object matrix by using this transformation matrix, this calculation, but it may take a longer time and very much complicated. So we use the deep neural network for learning this transformation, and also that is the decoding process by using deep neural network. Meanwhile, this generator stores the sequence, the trajectories of this demonstration. So here, Battle and Cup, so he shows some demonstration on several places. That is the pepper. So these, these trajectories are stored like that one into this recurrent neural network. That is the unfolding of time, recurrent network. So that is the trajectory generated by the trained, procedural memory network. So these trajectories are used for the robot for doing this, behavior. So that is the procedural memory. So earlier we calculate. The robot has to calculate inverse and forward kinematics for calculating, these trajectories. But in here, by using procedural memory, it can get the trajectories immediately without any calculations. That is advantage of using procedural memory. So in here, the robot is retrieving the trajectory between vinegar bottle to the part over there. So this trajectory is immediately retrieved from the procedural memory. Of course, this task sequence is retrieved from its episodic memory. But as I already told you here, the next step is pepper and the part. If those two objects are recognized, and then immediately retrieves the trajectory without any calculation. So that is the advantage of using procedural memory. So here, that is the pepper and sprinkled into the part like that one. So that is the advantage of using procedural memory without any calculation. That is the point. And motion planning, nonetheless, is needed, thinking of the collision avoidance. So we use this proposed QRLT star, and that is the octomap. So in this 3D map, by using the QRLT star algorithm, the path planning, motion planning are gonna be applied. So here, So here, so that is the RLT star. The other one is the, QRLT star. So you can see here, that is the obstacle. You can see this trajectory. So already almost done. But if you want to use conventional RLT star, it takes a longer time. So still try to grab the this red one over there. So this QRLT star is much faster and less computation time. So we use this motion planning algorithm, QRLT star, just for checking the collision avoidance. So here we use that motion planning algorithm for closing the water tap. Just because water is coming out from the tap, so it tries to close the tap over there. Before that, it has its internal simulator So the trajectory has been confirmed free of any collision with the obstacles, and then close the tab over there. And then the second step is this garbage disposal. So before that, again in here, in this Octomap, the robot tries some some trajectories over there, internal simulator. After confirmation, it tries to hold that one and grasping the other bottle over there, and moves back to this trash box. So that is the motion planning. And nonetheless, we need task planner, thinking of the task failure over there. I mean, the task sequence are going to be retrieved from this deep ART, episodic memory. Again, it, confirmed, the trajectory going to be confirmed in its internal simulator. If the task is failed, and then by using fast forward planner, the alternative task queue going to be selected and tested if confirmed, and then executed. So that is the adaptive task performance by using the task planner. So here, oops, sorry. Okay, it's a serial service task, servicing task. The problem here is two obstacles over there, pepper and green box over there. So it couldn't do the task properly. I mean, serving that cereal. So firstly, it tries the using task planner. Firstly, it moves the pepper over there, empty location, and that one should be also placed to the empty location over there. And then it follows the original task sequence from the DBART. So that is the cereal and then milk. So the task sequence could be retrieved from its episodic memory. So anyhow, in this task failure case, this task planner is needed. The next issue is agent embedded robot. So for this purpose, I did this research first, 3D agent with digital DNA. From his smartphone usage, we can get his personality features. And from his 2D photo, we get the appearance 3D features. And also from his voice, we get the phonetic features. Those three features are encoded into the DNA. And here, in this agent store, there are some, avatars or 3D agents provided there and downloaded into, for example, your smartphone, and into here, digital creature engine, and then you can have some interaction with this agent. So for this purpose, this digital, personality DNA, by using the QANN, we get features from the smartphone data, and also from the voice, we get phonetic DNA, and also by using those coefficients, you can create this kind of 3D agent. So eventually, you can build, you can model, you can generate this 3D model. So here, this Gangnam Style Psy, almost similar. That is, she is a figure skater, Jong-Hwan Kim, and he is one of my former students, almost same. From this 2D photo, This 3D agent could be generated. Those two are the movie star in Korea. So, okay, so this one could be used like this way. So that is the I Know Your Face. Famous K-pop star IU. Do you want to know my name? I'm hungry. He said, I'm hungry. Do you want to know my name?
그래.
Yes.
새 노래 나왔다며?
And now in here, multimedia could be used in here. I'm happy to hear that.
관심사가 뭐지?
That is the 3D agent. So this agent could be used in a robot. So like that one. 3D avatar is embedded in the MyBot. So that is the open-minded one. That is the agreeable one. That is somehow sensitive one. So depending on their personalities, its greeting reaction is different. So that is the agent embedded robot. And actually that is the internal architecture of this of the MyBot. So for the free talking, voice detection, speech recognition, and so on and so forth, and the cloud application, those three modules are activated so that here. Hello? Hello, how are you?
너 지금 기분이 어때?
I don't feel good because you bug me. Oh, I'm so sorry.
내일 우리 뭐 할까?
What do you want to do tomorrow? I'll give you a chance to decide.
뭘까?
What do you want to play? Let's play with blocks.
그래, 내일 보자.
Don't leave, I'll cry.
울지 말고 내일 보자. 너 여자친구는 있니?
Do you have a girlfriend? Yes, and she is pretty.
여자친구 이름이
Who is she? She is you.
고마워, 내일 보자.
And it's a real-time operation.
Where is it?
It's a visual question
What is next to the
answering, VQA interaction. What is next to the microwave over there? Toaster.
토스터.
Where is the yellow cup?
쉘프.
Is there a white cup on the shelf?
Yes.
What color is the kitchen cabinet?
Brown.
Is there a red cup on the shelf?
He's laughing. No. No red cup there.
No.
No.
What is next to the kitchen cabinet?
Refrigerator.
How many refrigerators are there?
Two.
What color is the kitchen cabinet? What is it?
Milk.
What are they?
What are they?
Cups.
Cups.
How many cups are there?
Four.
And now, based on this weekly interaction research, we're going to do more by
How
combining
many yellow
navigation
cups are there?
and task performance as well. So for that purpose, we confirmed this capability of VQA.
How many blue cups are there?
One.
So the next one is the Xiaomi's robot. As you can see here, two heads over there. So a sensor, an action, and reward. So that is applied to here. I mean, developmental episodic memory that was trained by using the simulation data from this DOC-MOT, as already introduced in the earlier part. So that is the simulation experience going to be used for training this episodic memory for both parts. That is the individual 1 and the individual 2. And then for the perceived information, they suggest action along with reward. And then through the coordination scheme, either winner take all or cooperative coordinated behavior is selected. So the ownership of the arms and body are going to be decided through this coordination. So that is the multi-human robot interaction using Xiaomi's robot. So that is the individual 1 and that is the individual 2. The advantage of the hardware design of my board is the hip joint over there. So this, so that is the, blocking behavior, blocking gesture. So people are gone, they are gone whenever the robot, blocks them. So after learning process, it recognized that the, blocking behavior gesture is not so good. So with a happy facial expression and, soft, the waving left arm like that, one move forward to have more interactions with him such that the robot can continue the interaction. And the other issue is experience transfer. So the experience from this individual 2 going to be transferred to the individual 1. So that is the friendly expression. So happy, face, and and this experience transferred to the individual 1 over there. So as soon as the individual 1 detects this person and shows the similar patterns, and we could try with the different characteristics. One is the agreeable one. So it enjoys the interaction with the students over there with a happy face and move forward. But that one is the timid one. So it feels some fear and blocking behavior. I don't wanna to get along with you and move backward. So that is the timid one. The other one is the agreeable one. So that is Xiaomi's robot. So by using the different DNA code for the personality, it shows different characteristics. And the last issue is this one, AI World Cup. So going to be held at KAIST December 1st we provided 3 categories. One is AI soccer game, and commentator, and the reporter. So we provide those, time schedule. So actually last week, before I came here, we could provide this, video clip. That is the Team Red and Team Blue. That is the random motion without any idea of playing this game of soccer. So we use DeepQ network for this Team Red, but get stuck into the local minima, and with this untrained DQN, and that is trained DQN Team Red against Team Blue, still random walk. So as you can see here, after the learning process, it knows how to play the game of soccer. So here, eventually we get a goal over there. So it's a multi-agent machine learning system in a dynamic and adversarial environment. So after this game, this one, Team Blue is also trained against Team Red. Trained one, and Team Blue has been trained against this red team. So they are playing the game of soccer, and 2 teams are very much competitive. So that is the initial stage of learning. So if we invest more time for learning those 2 teams, and then we could see the more skillful, plays between 2 teams. So now, if you're interested in this game, please contact me, jhkim@KAIST, ACKR. So that is all about my talk. And thank all my lab members. Thank you.